Hello, this is Tim Pavlak with another example of ANSYS Workbench in action. In this session we'll be using the mechanical application available in release 12.1 to study the performance of a Stirling engine. First we'll take a look at kinematics, then rigid body dynamics, natural frequencies, and finally flexible body dynamics. All of these simulations will be performed within the same simulation environment, that is, the mechanical application. Before we get into the various simulations we'll be performing, let me define the engineering definition of the problem. Here you see the Stirling engine mechanism and the rigid body dynamic analysis, but I'll just be using this analysis to describe the problem. The mechanism is made up of 9 parts. Looking in the worksheet, I see that all of the parts are assigned steel material. I also see that the stiffness behavior is currently set to rigid for all these parts. I'll be changing some of those stiffness behaviors in the other simulations. Next, let's take a look at how these parts are connected. There's a variety of connections, including a number of joints holding the parts together such that the mechanism is completely defined. There's also a number of springs, namely 2 springs in this model that represent the thermal cycle in a Stirling engine. One spring is between the large cylinder and the cylinder housing, and the second spring is between the 2 cylinders. These actually represent that cycle in the Stirling engine that induces the loading. Finally, in terms of the loading that we're going to be studying in a number of the simulations, we see here that there's going to be 2 load steps. The first load step imposes a 360-degree rotation, and the second load step releases that rotation and lets the engine progress in its natural mode. Now let's jump into the first simulation. Switching over to this window where my kinematics analysis is set up, I open the connections folder and I click on a joint that's set up such that I can perform the kinematic study. Issuing the configure button, a triad appears, and now I'm able to exercise that mechanism by means of this triad interactively using a kinematic solver. You see the mechanism is responding to my motion. I can control the motion in individual degree increments, as you see me doing here, 10-degree increments. I can also impose a fixed rotation in this kinematic analysis, such as moving it 180 degrees, and it jumps to that position. So this is the first simulation that we've performed in this mechanical simulation environment. Now let's take a look at the next simulation I can perform within mechanical. Jumping back to the window where the rigid body dynamic analysis is defined, I see that the solution is complete. Clicking on the individual results that are present, I see how they vary as a function of time. We were looking at total deformation. Now I've selected a joint probe which displays joint force, and you see an arrow in the screen. That arrow is now animating, showing how the magnitude of that joint force changes as a function of time. And the springs are working and the cylinders are moving. This gives me a good feel for rigid body dynamics. Next we'll take a look at another behavior for this mechanism considering flexibility. Here we are inside mechanical with a modal simulation set up. This mechanism is the same as the other simulations we've performed so far, only this time there's an additional flexibility included. In addition to the springs, the crankshaft has been set to flexible and is discretized as seen in this picture. In this modal analysis I'm going to be studying the first 12 natural frequencies. The first one is basically being driven and specified by that spring and the free rotation of the mechanism. And you can see here that the crankshaft is rotating in this first mode. The next natural frequency is 53 Hertz, as shown here in the tabular data view, and this one shows that the crankshaft flexibility is coming into play. It's actually bending quite a bit, and that will have an impact in any flexible body dynamic analysis we'll perform, which we'll do next. Here we are inside mechanical with a flexible body dynamic analysis complete. I'm going to animate the deformation solution, and you'll see how the mechanism is experiencing quite a bit of flexibility. And the first load step where the imposed rotation is applied, it rotates, but then in the next load step where that imposed rotation is relaxed, the flexibility dominates so much that the mechanism doesn't progress as expected. So we'll try and change the model a bit to improve that behavior in the next simulation. Next, let's jump over to another version of this flexible body dynamic analysis where I've increased the size of the crankshaft. Here you see that the rotation progresses as expected beyond the point where the imposed rotation is released and the mechanism continues in its rotating fashion. Here there's not the oscillation I saw in the earlier flexible body dynamics analysis. I can also take a look at stress as a function of time, and now you see the stress values, the maximum stress value, oscillating, and that's due to the flexibility and the high frequency content that's present with this flexible parts defined in the model. See how the stresses oscillate as the mechanism progresses through its loading sequence. These could be dampened out with some opposed damping later in the analysis or in a subsequent analysis. And finally, wrapping up and completing the picture, here you see a joint force animation on the same joint we looked at before, only this time that joint force is oscillating more, again due to the flexibility of the crankshaft. So that wraps up our various simulations. Next we'll take a look at what we've studied in this session, and we'll wrap it up. Taking a look at the project page for Workbench. Here this shows that we've performed 5 simulations: the kinematics, the rigid body dynamics, modal, flexible body dynamics, and a second flexible body dynamics with a larger shaft. We could have gone on to study damping, study this mechanism with nonlinear materials or nonlinear contact. We could have also performed several additional simulations such as explicit dynamics, random vibrations, even a thermal analysis. But let's leave those for a future session. Look forward to showing you something new next time. Have a great day.